Now, frequently when we're dealing with thermodynamics, we're dealing specifically with gases. There is a thermodynamics that exists as far as I said, expansion of liquids or expansion of solids, etc. But we primarily are dealing with gases. When we talk about gases, there are three primary things that drive how a gas behaves. Okay, one of them is how much gas you have. One of them is how much volume of gas you have. Okay, how big is your container? If we talk about this room, and I was to say, well, it's 5 meters in that dimension, 8 meters in that dimension, 3 meters up and down, you multiply all those together, you get the cubic volume that I have, cubic meters that I have, and that would be a volume. Okay. Now, in this particular room, we're sitting on the earth where the atmospheric pressure is whatever it is, but I could take all that gas that's in this room, and if I had the right compression materials, I could put that all into a tank. Everybody's seen like scuba tanks and things like that, oxygen tanks. So we can take that gas and we can compress it. We can't do that with liquids. Liquids are what's called incompressible. But when we talk about gases, very easy to compress them. So the pressure that we put on, we can squeeze these things, and that's a pressure, and different pressures also impact gases. And a third thing that has a lot of impact on gases is temperature. And I alluded to that with things like solids. There's that expansion and contraction type thing that is related to temperature, but even more important when it comes to gases. So the temperature of the gas, basically, if you think about this gas as just being a little ball that's floating around in the air, the hotter it is, the faster it moves. And so if it's moving faster, then it has more collisions with the other gas particles that are around. Everything heats up, there's more stuff going on. So those are really the three big important factors that come into play. Now, if we are talking about a case where, let's say we're able to keep the temperature constant, it turns out that if we keep the temperature constant, then this will be true, okay? So we have an environment where we've got this gas, we keep the temperature constant, and if we change the pressure, so again, how do we keep the temperature constant? Well, let's say, for instance, we're in this room, it's roughly 25 degrees Celsius. We have a container like this. We put, not exactly a lid on this container, we put a lid that seals here, so it's a piston in that container. And we don't do anything else. We've got these particles of gas that are in here. We don't apply any heat or anything, but we push this piston down a little bit. Now what's going to happen when we push that piston down is if we don't let any of these gas particles get out and push this piston down to here, we're going to have a higher density down here, right? So what's going to happen there? Our volume decreases, and when our volume decreases, our pressure is going to go up. And that's what the equation up here says, is it says the product of these two is going to be a constant. So if this one goes up, this one has to go down, or vice versa. If this one was to go down, this one would have to go up. They have to keep that constant, provided that the temperature is constant. And that rule right there, that's known as Boyle's law. And that's when you keep temperature constant. Now, if you don't keep temperature constant, and instead you keep the pressure constant. Okay, so I'm going to say keep pressure constant. When the pressure is constant, it turns out that the relationship is like this. So again, starting with this, say, okay, I'm going to keep the pressure constant. So what does that mean? That means right now atmospheric pressure is pushing down on this, and let's make that piston so that it's free to move, and this is a cylinder that it can move up, whatever. But atmospheric pressure is pushing down everywhere, okay? So if the atmospheric pressure is pushing down and this thing is free to move that way or that way, and I introduce a flame under here to heat this whole thing up, now what's going to happen? The temperature is going to increase. Temperature increases. If this thing is able to go up, then it's going to push up, and my volume is going to change because the temperature increased. And even though these particles are going to be warmer and moving around more, they're not going to have more collisions than they had here, because basically they lift that up, and the pressure is the same out here as it is out here, so the pressure is constant. And so this says, if you've got some fixed space where you can keep the pressure constant, if the volume goes up, it's because the temperature went up, or you can have the volume go up and the temperature will go up, volume goes down, temperature goes down, but that different, or that quotient there is going to remain a constant. That's called Charles' law. I guess I should have erased the first one. Let me make room to write all these things here. Boyle's law is P1 V1 equals P2 V2. Charles' law is V1 over T1 equals V2 over T2. Now the other thing that we could do is we could keep the volume constant. If we kept the volume constant, it turns out that we would have this. P1 over T1 equals P2 over T2. And that's known as the Guy-Lussac law. Now, what situation am I talking about here? Okay, now I'm talking about, I've got the same conditions that I had here before. I've got this piston in here. I've got particles down in here. But now I weld this so it can't move. And now I introduce heat under here. Temperature goes up, this is going to heat up, things start moving around faster, pressure is going to go up. So as the pressure goes up, temperature goes up. Pressure goes down, temperature goes down. Okay? So I can have, as long as I can keep something constant among those three items, then those are the three different laws that govern it. But they're all subject to this. They could all be changing. And one way to write that would be like that. So if I say, well, my pressure changes by a little bit, my volume changes by a little bit, and my temperature changes by a little bit, then I can calculate how much those changes affect each other. Okay. Another way that this is more commonly written is that people will say, well, if this is, these things are equal, then that the whole thing is equal to a constant. So I can rewrite this as P times V equals N times R times T. And you've probably seen this if you've taken a chemistry class. Sometimes they talk about this as being Pivnert, okay? Where in this equation, we've got pressure, volume, temperature. Then this is the number of moles. N is the number of moles. And R is something called the ideal gas constant. And the ideal gas constant has a value of 8.31 that allows us to, so that's truly a constant, 8.31 joules per mole degree Kelvin. And this is assuming, if we fix the number of moles, in other words, it's in a closed system, then this is the relationship these things have. Now, if we can change the number of moles, of course, the number of moles goes up and everything else is the same. If we can inject some gas into a system, then that's going to have an impact on other things within the system.